Hello, this is John Miares, and in this lesson, we're going to take a brief look at the graphs of tangent, cotangent, secant, and cosecant functions. I do not plan on getting into as much detail as I did for the sine and cosine graphs, as the real-world applications to these functions are much more limited than they are for sine and cosine. To that end, we'll focus on just the basic shapes of these graphs, then look at a few examples which focus on transformation of the graphs using the basic shape method. In total, this presentation only has 11 slides, one of which is the title slide and one of which contains the problem challenge problems at the end. So I'm hoping that this presentation will be considerably shorter than the last one. We'll start by looking at the function of f of x equals tangent of x. One thing that you should notice right away is that it does not have a wave pattern like the sine or the cosine do. We know that the tangent of 0 is 0, and as we go around the unit circle, you're looking at the ratio of the opposite side to the adjacent side. In quadrant 1, both of those values are going to be positive, so the values of the tangent function will also be positive. As the opposite side gets larger, the adjacent side is going to get smaller. So the ratio opposite over adjacent is going to get larger. At 45 degrees, or pi over 4 radians, the ratio comes out to equal 1, since the opposite side y and the adjacent side x will have equal lengths. As the Mangel measures approach 90 degrees, what you're going to see is that the opposite side of the unit circle is going to approach 1, while the adjacent side, x, approaches 0. When you divide a number close to 1 by a tiny decimal close to 0, the values get huge, essentially approaching infinity. At 90 degrees, or at pi over 2 radians, what we see generated here is a vertical asymptote, because you are dividing an opposite side of 1 for y by an adjacent side x having a length 0. 1 divided by 0 is undefined. Graphically, we see this vertical asymptote generated at 90 degrees, or pi over 2 radians. As we head into quadrant 2, the opposite length is going to be positive, but the adjacent side is going to be negative. So the tangent ratio is going to divide out to be negative. As x gets closer to 180 degrees, the opposite side is going to get smaller and smaller, while the adjacent side gets larger and larger until you get to 180 degrees, where the opposite side y will equal 0. So the tangent of 180 degrees, or pi radians, will be 0. In quadrant 3, both the opposite side and the adjacent side are going to be negative. So their ratio, opposite divided by adjacent, y over x, will come out positive. As the angle measures approach 270 degrees, the opposite sides again are getting larger, while the adjacent sides getting smaller, both in the negative direction, until you get to 270 degrees, when the adjacent side is 0, making the tangent function undefined again, which would create another vertical asymptote here at 3 pi over 2, or 270 degrees. Finally, as we head past 270 degrees into quadrant 4 towards 360 degrees, the opposite side lengths are negative, the adjacent side lengths are positive, making the tangent values come out negative. And as we get closer to 360 degrees, or 2 pi radians, the opposite side is getting closer to 0, while the adjacent side, x, is getting closer to 1, making the ratios all get closer to 0. At 2 pi radians, the pattern is going to start all over again. Now let's look at the properties of this function. The domain of this function is not going to be all real numbers this time, because the function has those periodic asymptotes that are going to occur whenever the adjacent side x has a value of 0. This is going to happen at 90 degrees, 270 degrees, and at any angle coterminal with them. To simplify the notation, Rather than attempt to describe the domain in interval notation, what we would probably say is that the domain of this function consists of all real numbers except odd multiples of pi over 2, which would include pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, and so on, both in the positive and negative direction. The range of this function actually will include all real numbers between negative infinity and positive infinity. Unlike sine and cosine, which each have the hypotenuse in the denominator of the fraction, the tangent function is relating two side lengths that can range anywhere between -1 and 1. So when you divide all possible pairings, you can get pretty much anything you want. As for symmetry, we should be able to see that this graph has symmetry through the origin, making it an odd function. Looking at other patterns in this graph, we can say that yes, it does pass through the origin, but the repeating pattern, or the period of this graph, is actually 180 degrees or pi radians instead of 360 degrees or 2 pi radians. This is a unique feature of both the tangent and cotangent functions. The asymptotes are going to occur at odd multiples of pi over 2, which if I want to describe that pattern with a formula, what I'd have to say is that they occur at every value where x equals 2k plus 1 over 2 times pi, where k is an integer. If you recall from our studies of sequences back in chapter 12, the formula 2k plus 1 will generate an odd number when an integer is substituted for k. So this formula will generate odd multiples of pi over 2. One last thing to notice is that this function never decreases. I don't know that it would ever be appropriate to say that it always increases, because certainly what happens as x approaches pi over 2 or 90 degrees as we travel from left to right, the values are spiking upwards towards infinity. Then when we get into quadrant 2, the values of this tangent function down here miraculously reappear as negative and then start increasing again until we get to 270 degrees when it's back at positive infinity. And then it shows back up at negative infinity just past 270 degrees and starts increasing again. Long story short, I think it's safe to say that this function never decreases. It is not good to say that this function always increases. The cotangent graph has some very similar features to the tangent graph because tangent and cotangent are reciprocals of each other. You might think at first glance that the cotangent graph is just the tangent graph flipped upside down, but that is not the case. Remember, the tangent of 0 is 0, but the cotangent of 0, its reciprocal, is going to be undefined. So wherever the tangent values were 0, the cotangent is going to be undefined. Similarly, wherever the tangent values were undefined because I was dividing by 0, the cotangent values are going to equal 0 because now what we have are zeros in the numerator instead of in the denominator. Also, since tangent and cotangent are reciprocals of each other, they're going to have an inverse variation relationship between them. So as the tangent values were always increasing, the cotangent values are always decreasing. Let's look at some of the properties here. Cotangent does have periodic asymptotes like tangent does, but just not in the same places. Here, those vertical asymptotes are going to occur at every whole multiple, or rather integer multiple of pi, including 0, pi, 2 pi, 3 pi, and so on, both in the positive and negative direction, negative pi, negative 2 pi, negative 3 pi. The range, like the tangent, will be all real numbers. As for symmetry, this function is going to be odd as there is symmetry over the origin. Even though the function doesn't go through the origin, it should be visibly clear that for every point xy that is on this graph, there is a corresponding point negative x negative y also on this graph. This is going to have a pattern of repeating itself just like tangent every pi radians or 180 degrees, with periodic asymptotes at the integer multiples of pi. Similarly, in a way that tangent never decreased, the cotangent function is never going to increase. Now we're going to look at the secant graph, which is a bit more unusual. If you think about the secant, the function is the reciprocal of the cosine, which means where the cosine, adjacent over hypotenuse, could never be greater than 1 or below -1, the secant function, hypotenuse over adjacent, can never be less than 1 or not between -1 and 1. Here is a graph of the secant function with various points labeled between 0 and 2 pi. Now, as we look at some of the features here, we're actually going to see that the domain is going to be the same as the tangent, where the domain consists of all real numbers that are not odd multiples of pi over 2, because those are where the values of the adjacent side, x, are going to be 0 as we draw our reference angles around the unit circle. The range, as noted earlier, is going to consist of all real numbers not between -1 and 1. In interval notation, it will look like real numbers from a low of -infinity to -1, close the bracket, and then in union with all numbers greater than or equal to -1, all the way up to positive infinity. As for symmetry, this graph is going to be symmetric to the y-axis, making it an even function. This is consistent with the cosine graph, which is also an even function. Looking at other patterns, the secant is the reciprocal of the cosine, which you may not see much of a connection to until I insert a graph of the cosine with the graph of the secant. Notice when the cosine equals 1, the secant will also equal 1. As the cosine values decrease towards 0, the y values for the secant graph are spiking towards infinity. When the cosine equals 0, the secant function, its reciprocal, is going to be undefined. When the cosine goes negative, so does the secant. And again, when I get down to -1 on the cosine, the secant will also equal -1. Oftentimes, when I'm asked to sketch a graph of a secant function, I often first look at the cosine graph and know I can get the basic shape of the secant by drawing these patterns away from the cosine humps, knowing that they touch each other at y equals 1 periodically, or y equals -1. The cyclical pattern is going to repeat itself every 2 pi radians or 360 degrees, where you have something that looks like an upward opening parabola here, followed by this downward opening parabola, and then it's going to start itself over again. It is important to note, though, that these little pieces of the secant graph are not parabolas, as parabolas are not supposed to ever be bounded between asymptotes like these are here. Finally, just like the tangent graph, the periodic asymptotes are going to occur at odd multiples of pi over 2. The cosecant graph has a lot of similarities to the secant graph, which, when you think about it, should make sense since a sine wave and a cosine wave are very similar to each other too. In fact, if you took a cosine wave and shifted it to the right by pi over 2 radians or 90 degrees, you'd get a sine wave. This is no different. Essentially, look, this is going to look like the secant graph, but everything's been shifted over by pi over 2 radians or 90 degrees. Looking at the properties, the domain this time will follow more what we saw with the cotangent, in that it will be all real numbers except integer multiples of pi, where the function is going to have these periodic asymptotes. This is because, like with cotangent, those are where the values of y, your opposite side that you're dividing by, will equal 0 in your reference triangles. The range, like secant, will be all real numbers except those between -1 and 1. Looking at symmetry, this function, like the sine function, will be odd, as any point xy on our graph up here will be mirrored through the origin down here with the point negative x, negative y. As for other patterns, the cosecant is the reciprocal of the sine function. So if I was to draw a sine wave alone with the cosecant graph, then what you'd see is the reciprocal behavior that was happening just like we had between cosine and secant, where sine equals 1, cosecant equals 1. As the sine function values get smaller, the cosecant values get bigger. When sine equals 0, the cosecant becomes undefined. The pattern will repeat itself every 360 degrees or every 2 pi radians, just like with sine and secant. And the periodic asymptotes this time are going to be at integer multiples of pi, just like the cotangent. If you were asked to transform tangent, cotangent, secant, and cosecant functions, the basic shape method we looked at in the last section will generally apply as expected. Let's define our function t of x as one of the four trigonometric functions that are not sine or cosine. So t of x could be tangent, cotangent, secant, or cosecant. If you are looking at the function a times one of those trig functions, t, of b times the quantity x minus c with a plus d on the end, then the coefficient a is going to affect the steepness of the graph, just like it did when we were looking at sine waves, cosine waves, and even parabolas in general. And we can even say that changing the sign from positive to negative is going to flip the graph upside down. But because these graphs do not have a wave pattern, it would not make sense to call the A value the amplitude this time because that term is explicitly used to describe wave patterns. The B value in front of the quantity x minus c can still be thought of as the frequency in that it still affects the length of the period indirectly, but it behaves a bit differently for tangent and cotangent, as the standard period for those graphs is only pi radians or 180 degrees, while the standard period for secant is 2 pi radians, same with cosecant. The C value, just like with the other graphs, facilitates a horizontal shift or a left-right shift. And the amount of that shift can be determined properly so long as the B value is factored out. If you see a problem where the B value is not factored out, then you should factor out the B value first so you can determine the magnitude of that horizontal shift. Finally, the D value on the end is going to cause a vertical shift. I wouldn't necessarily call that value the axis of oscillation because the graph doesn't oscillate like a sine or a cosine wave does, but you could call it the axis of equilibrium. Again, although we can see similar behavior to the amplitude, the phase shift, and axis of oscillation in these graphs, we don't call them that because to do so would imply that the graphs have the shape of a wave, which they do not. The only term we might carry over from sine and cosine will be the frequency b and the period lambda. Now let's look at a few examples where we would apply the basic shape method to the tangent function. Suppose we want to compare the graphs of y equals tangent of x to y equals the tangent of 4x. Here is one cycle of the y equals the tangent of x, running from negative pi over 2 to positive pi over 2, with key values plotted along the way. Remember, the tangent of pi over 6 is the square root of 3 over 3, tangent of pi over 4 is 1, tangent of pi over 3 is the square root of 3. Here, these values are labeled with their decimal equivalents because, well, I couldn't get Desmos to label them in simplified radical form. The period of the tangent graph is going to be pi, and the 4 in front of the x in the second function will cause the standard period to be divided by a factor of 4, making the new period now pi over 4 to complete one cycle. You could also say that in the same horizontal distance of pi, you should be able to get 4 full cycles of this graph constructed. So here is a graph of the tangent of 4x. I didn't label all the points, but you should be able to see the y coordinates do correspond perfectly to the basic shape, the red graph on the left, just the x values have all been divided by 4. Similarly, if you look carefully, what you should see is that we do actually have 4 full cycles of the tangent graph constructed between negative pi over 2 and positive pi over 2, making each of these pieces of the curve have a length of pi over 4 horizontally before hitting asymptotes, which I have not drawn in here. Let's look at another one. Here we want to compare the graph of the tangent function to the graph of the tangent of the quantity x minus pi over 4. Again, let's look at our basic shape of the tangent graph with a period of pi. For the tangent of x minus pi over 4, your graph is still going to have a period of pi, but everything is going to be shifted over to the right by a factor of pi over 4. So your graph is going to look something like this. Again, you can see all of the y values in this function correspond perfectly to the basic shape, but now the x values have all been moved to the right by a factor of pi over 4. To get some of those x values computed by hand, you might have to use some common denominators to move things over. For example, the pi over 6 plus the pi over 4 will get you 5 pi over 12, while pi over 3 plus pi over 4 will get you 7 pi over 12. The vertical asymptotes, which were at odd multiples of pi over 2, have also been moved over to the right by pi over 4. So this one here is going to be at negative pi over 4, and this other asymptote will now be at 3 pi over 4. Now let's look at a couple involving secant. In our first example, let's see what happens when we want to compare the graph of y equals the secant of x to y equals 3 times the secant of 2x. I've drawn one cycle of the secant graph here with values ranging from negative pi over 2 up to 3 pi over 2 on the x-axis. I did it this way because splitting it between 0 and 2 pi is going to be much harder to see and to visualize. The period of the secant graph is 2 pi, but when you look at the period of y equals 3 times the secant of 2x, it gets cut in half because of the b value equaling 2 in front of the x. Additionally, the 3 in front of the secant is going to make the y values 3 times steeper than they normally would be. This is going to make the graph of our final function look something like this, where instead of starting at the point 0, 1, I'm at the point 0, 3. And then the values on the lower parts of the graph peak out at y equals negative 3, and they work their way down from there. You can also see that these parabolic shapes are more compressed, and the asymptotes are occurring at odd multiples of pi over 4 instead of at odd multiples of pi over 2. This is the result of the b value equaling 2 in this function. The basic shape remains the same, but the 3 makes it taller and the 2 makes it skinnier. Let's look at one more. This time we'll look at the secant of the quantity x plus pi over 3. Again, we'll look at our basic secant shape for comparison purposes, and we see that it has a period of 2 pi. The second graph will also have a period of 2 pi because the b value will equal 1. And it won't be any steeper than the basic shape of the secant graph because the coefficient in front of the secant function is still 1. What the pi over 3 inside the parentheses is going to do is move the entire graph over to the left by a factor of pi over 3. So your graph will look something like this, where the graph originally had points at 0, 1, the new graph is going to have a point at negative pi over 3, comma, 1. All the corresponding y values are the same, and the basic shape of the graph remains the same, but all of the points and all the vertical asymptotes have been shifted to the left by pi over 3 radians. Okay, that's all I really wanted to cover here as far as content. Hopefully this wasn't too painful for you, or worse, too fast for you. There is one last thing I do want to do, and that is show you how we can graph secant, cosecant, and cotangent on your calculator since your calculator does not have a secant button or a cosecant button. All right. So for this part of the demonstration, what I'm going to do is use my graphing calculator emulator on my computer to look at the cotangent, secant, and cosecant functions. First thing we need to double check is to make sure that I am in radian mode. So I'm going to hit my mode button. And this one does say having highlighted the radian. If it does not work, I can just use my down arrow and then hit enter, and that will switch it over to radian mode. Now, in order to graph this function, let's say I want to start with the cotangent of x. The cotangent is the reciprocal of the tangent. So what I'm going to have to do is enter this in as 1 divided by the tangent of x. And I'll close my parentheses here. I do not want to use this tan to the minus 1. Again, that means inverse tangent. That does not mean the reciprocal of the tangent. Now, the second thing I'll need to do in order to get my window set properly is I'm going to go to the zoom menu and I'm going to choose option 7, Z trig. This is going to set a window that is going to be ideal for tracing values on this graph, knowing that what I'm working with is a trigonometric function. So now as I hit enter, I'm going to be able to see this pattern with the cotangent. It is not going to show you the vertical asymptotes that are there, but they are there nonetheless. If I hit the trace button, you can see when x equals 0, y equals nothing. If I use my arrows, I'm going to be able to follow this along, and I'm going to get to pi over 2. I'm going to get this decimal that says 3.7949e minus 9. That basically means 0.00000000379. Essentially, the calculator is having some round off errors when it comes to evaluating this, but really this value should be 0. As I keep tracing to the right, again, you're going to see this thing is going to decrease, and eventually at x equals pi, 3.14159, again, small round off errors, it's saying y equals 1.6955 e to the 9, which is really negative 1.6 billion. It's supposed to be negative infinity, but again, I can't get technology to work perfectly for me in this case. So that is how we're going to look at the cotangent graph. For the secant is the reciprocal of the cosine. So I'm going to clear this out. I'm going to say it's 1 divided by the cosine of x. And I will hit enter, and I'm going to graph that. And there is my secant graph. Again, if I hit the trace button, I'm at 0, 1. And then I can use the arrow keys to go up. It will reappear over here and go down, and then reappear over here and go back up. Now, if we were to do something fairly complicated, like if I wanted to do 3 times the secant of 2x, what I'm going to have to do is I'm going to have to change this to a 3 here, and instead of saying divided by cosine of x, I'm going to change this to say cosine of 2x. And then I'll close my parentheses. So this is going to be 3 times the secant of 2x. I'll go to graph that. And again, you're going to see that behavior that we saw before, where it's starting at 0, 3, and then going back down here to negative 3. But we still have these periodic asymptotes, which are going to show up more frequently now. For the cosecant, the difference is that it is the reciprocal of the sine. So I'm just going to now use the sine command, and I will get rid of that coefficient there. And then here is going to be the cosecant of x. So that's pretty much all I wanted to show you on here, so that you can use your calculators to generate the secant, cosecant, and cotangent. Do not use the sine minus 1, cosine minus 1, and tangent minus 1. Those are for inverse trig functions. We're going to explore those in sections 5.5 and section 6.4. But for now, for the reciprocals, just make sure you're doing 1 divided by the particular ratio that we're looking at. All right. Like I said earlier, these functions don't have a lot of the fancier applications in the grander scheme of things. But it is important that you know what these basic shapes look like for these functions, and you should be able to generate a simple graph with these applying the basic shape method. And now you've also seen how we can do them on your calculator. Here are the problem challenge problems for section 5.4. If you have any questions or any worries about them, feel free to contact me via email or post your question on the discussion board. Thanks for watching, and we'll see you all soon.